Okay, good afternoon, or good morning, depending on where in the world you are. Welcome to the 6th session of the Sunoikisis Digital Classics fall program from 2016, which is Digital Ancient History and Archaeology. This is the third of 3 geography sessions, this one based on GIS, and this will be led by Leif Isaksen from Lancaster University and Alegria Perez from the School of Advanced Study at the University of London. And I will pass over to Leif.
Great, thanks, Gabby.
Great. Cheers.
Okay, I can hear a bit of echo, is that okay? No, that seems to be, I think it may be in your speakers or something. Okay, here we go. So, here we go, see if this works. And share. Is that looking all right? Does that seem to work okay?
Yes.
Yes, that looks fine.
Great. Okay. So yeah, it's great to talk to you all about Geographic Information Systems, or as Gabby said, there's some disagreement about whether GIS should stand for Geographic Information Systems or for Geographic Information Science. And we'll be doing a little bit of both today. A number of the things that we will be talking about as well, of course, have come up previously in the earlier presentations, and that's no bad thing. As Tom said last week, this is a very large and ever-growing topic with lots to think about. So all we can hope to do here is to scratch the surface, to introduce you to some new ideas, perhaps reinforce some of the ideas that you've encountered before. And then hopefully welcome you into the wonderful world of geospatial technologies and what you can do with them, as well as some of the things to think about, some of the limitations, because ultimately we have to remember that we are also humanists and we should be driven by the questions, not merely the technology. I'll be doing this together with Alegria Perez, and I'll be handing over to her a little bit later on. So. This is a quick overview. We're going to first of all talk about why we might care about space. Then we're going to move on to a brief introduction to Geographic Information Systems. That's a particular approach to geospatial technology, which has a somewhat different history, even though it's heavily overlapping with some of the technologies that you've encountered earlier on in this course. Then we're going to see a little bit of GIS in action using a software package called Quantum GIS. It's going to be very simple, but just to give you a sense of what it looks like when you work with a GIS system. And then Alegria is going to give you some examples of what you can do with that. We're going to move on then just to think about some of the issues with using Geographic Information Systems. And then finally, if there's time, there's a few slides about where you might get started with data. If we run out of time for that, those slides will be made available, and there'll be there'll be information on the wiki where you can find some basic data sets. And then we'll move into questions and discussion time. So first of all, why space? Some of the technologies we've been looked at before, so of course, assume that you're interested in space, but it might be worth coming back and just thinking about some of the reasons for this. So it's important to distinguish between the spatial phenomena that we often try to represent within these technologies, and the fact that ultimately we're much more interested usually in the explanatory factors that cause those phenomena. So we're dealing in a sense with proxies for the things that we might be interested in. So we might be interested in clustered sites of criminal activities that are reported, for example, in the Old Bailey proceedings online, or a hierarchy of settlements within a region, or the way in which place references within a classical text have a sort of circular sequence where the author will talk about something, then move on to another space, and then move back again. Or we might be talking about the apparent zodiacal arrangements of monuments in the southwest of Britain. And of course, there could be a variety of possible explanations that that lead to that. The one I want to, these are just possible ones, but the one I'd really like to bring your attention to is the last one here, known as apophenia, which is the tendency for human beings to see patterns in spatial data, and that's a really important aspect of the way our brains work. One of the reasons we're such successful. Indeed, that animals develop eyes to be able to, and parts of their brain to be able to spot these patterns. But we also have to be aware that thing is always working, and when there are only random patterns of dots or any other phenomena, we do have a very strong tendency to read stuff into it, which may not in fact be there. So we want to use the power of our brains to detect patterns. At the same time, we don't want to be seduced or succumb to this unfortunate tendency. Working with geographic information is part of a wider field that we can think of as data visualization, where often we're really interested in placing things in a dimensional context. So in this particular case of geographic information, we're thinking about the physical space of the world, typically in 2 dimensions. But of course, we have to remember that the world is a globe, it's a sphere. So what goes around comes around, and within that sphere, there is, of course, altitude. So there is a 3rd dimension that we may want to take into account as well. In addition to that, there may be additional dimensions such as time and other kinds of classification that we want to associate content together with. And this is partly because of an intuitive understanding that phenomena that are closer together tend to be more related than phenomena which are further apart. And we're ultimately looking again for the underlying fields, the structure, the things that are causing these phenomena to pop up. So whilst we might be mapping particular points or representing particular columns within a histogram, ultimately it's the overall picture that we're interested in. We're not usually interested in some specific point in some kind of abstract space. So why is digital important? Why can't we get away with just using paper maps, which is of course what people have used for millennia, as we shall see? Well, the digital changes the game because it moves from what is quite literally a superficial practice where we are trying to map aspects of the world onto a planar surface, onto something with 2 dimensions. And although we can focus on different parts of that surface, ultimately we have to make very specific decisions about what's there, and we can't change those after the fact. When we move into the digital world, then we have the opportunity not only to have change through time, but we also are able to interact with that data. And that means through time, we actually have an infinite number of ways in which we might interact with that data, and the possibilities for visualization bifurcate through time. So when we're dealing with multiple dimensions, it's not in the way that this laptop seems to suggest, where there's some kind of solid reality or multidimensional reality that we're perceiving at once. But in fact, we're tricking ourselves by using that additional dimension of time and our ability to choose things in time that enable us to explore a much wider number of variables that we could explore if we were just using or just representing something on a planar map. Tom stole my thunder a little bit last week when he very rightly pointed out that Claudius Ptolemy is where this all begins. The geographic information systems are not in any way a new thing. So Ptolemy, way back in the 2nd century AD, was already taking data and giving it latitude and longitudinal coordinates, but storing those independently of their representation as maps. So he then gave instructions on how to draw maps with this data, and those different methodologies are different projections, and they're used for different purposes. So here is one of the examples which is if you want to be able to represent the world as a whole, whereas conversely, we might be interested in more what he calls chorographic representations, regional representations in which the maps could look different. And part of that is because of the problem of representing the sphere, and we're going to come to this problem later on, representing parts or all of a sphere within a single planar surface, which ultimately, of course, is what we're forced to do, whether we're using paper or working with a screen. A GIS, as its name implies, or at least one of its names implies, is a system rather than a specific software package. So it's best not, or you should ideally not try to think of GIS as a piece of software that you download onto your computer and where you do all of the work. Even though frequently you will find that you're doing a lot of the work within a particular software package. It's a system in the sense that it has input, we want to visualize and manipulate it, and it also has a variety of different ways in which we might output something. And we don't have to do all of those within one particular software package. So in terms of input, there are a number of different approaches that we might take and indeed combine a number of different approaches. So we might be going out into the field and recording content with something like a total station, or we might be taking a historic map and putting it in a scanner and taking what is essentially a digital photograph of something. And there are a whole range of different ways that we might bring data into our GIS, and we'll see some more of those later on. Once it's in there, we need some way of storing that, and that database may be in the form of files, or it may be a relational database, or it may be something different. And then we need tools that enable us to analyze and manipulate that data in different ways. And that's going to require an interface, or indeed multiple interfaces. There might be different views that we can have on that data. Once we've done that, there may be different ways in which we want to report and visualize that content through different mechanisms. The most conventional is, of course, going to be on some kind of map, but it could be a digital map. It could be the kind of web mapping interface that Tom was talking about last week, or it could be a paper map, or it could be something radically different. So if you think these days, many of us, if we're driving around, will be using some kind of GPS mechanism, and that will have a map, but it may also have some auditory mechanism. It's going to tell us, somebody's going to speak to us and say, turn left at the next light. And that's geographic information too. So we shouldn't restrain ourselves to think about geographic information purely in terms of the visual or tables, even if that's the way that we often are working with this content. So what does a geographic information system look like? There are probably three major ways in which the content within a GIS is worked with and visualized. The way that I imagine by now you will be most familiar with when you think about a GIS, if you've thought about it before, is some kind of map view. So this is going to have a map. And it will have the sorts of navigation tools with which you will certainly be familiar with from web mapping technologies like Google Maps, that enable you to pan and zoom in. It will have other basic tools that would enable you to interact with the content in the map. So you might want to identify a particular feature, you might want to find something, you might want to sort of search for it, or do things with a very spatial aspect to them, like measuring. And then there'll be a legend that will enable you to add in or select specific layers, much in the way that Tom talked about last week. Just as important for that to that map view, there may be there'll be views on the data. Most commonly will be some kind of table view, because GIS systems are generally based on a structure that is very similar to a relational database. So these will have columns and rows and enable you to select content within it. And usually there is a direct association between what's happening in a table view and a map view. So as you select content within a table, it can be highlighted within the map and vice versa. The table view is, of course, also the way most commonly that people will edit content that's within a geographic information system. And because when geographic information systems were developed, and indeed as is still the case today, there is always still a very heavy reliance on paper-based maps. And the way the paper-based maps work is quite different from the way in which we interact with data in an application. Not least of which, of course, is the issue of scale. So I can't measure part of my screen and then, based on some kind of standard ratio, make an assumption about how far in the real world a particular distance is. But with paper maps, we can do that kind of thing. So most GIS systems will also enable us to take the content that we've been working with within a GIS and convert that into some kind of formalized paper map that might be used out in the field or printed in a book or something similar. And that's going to require other kinds of furniture that are on the map as well, like scale bars or north arrows, grids, and the like. Data in GIS the data in a GIS could, in theory, be recorded in something like a relational database with lots of images stored within it. But really what we're interested in with the GIS is its ability for us to derive answers to spatial questions rather than having to store them in advance. So by storing, for example, information about a particular or several particular features, we could answer questions such as how big, if this is the boundary of a hill fort, we can ask, well, how we know where the line of the hill fort is, but we can calculate its internal space, for example. Or we can compare it here with Google Maps and detect, or at least visually detect, the nature of the vegetation within the hill fort. And perhaps if we had some other kind of data in there which recorded the nature of the vegetation or classified the nature of the vegetation, then we could automatically derive that. If we have a digital elevation model, we can see not only the elevation of the hill fort itself, but perhaps we could calculate its elevation relative to the average elevation of terrain that was nearby. And we can look at this is here composed of different lines. We might be able to identify within the earthwork what proportion of that earthwork is still visible versus the proportion which has been destroyed. GIS, the data within a GIS typically falls within two different categories of content. And whilst it's possible to convert between them to some degree, that is almost always a lossy process. You will lose data along the way in doing so. So you have to choose quite carefully when you're recording information, which of these different approaches you want to use. The first of the, on the right-hand side, you can see two examples of this, which are recording essentially the same phenomenon. So vector data assumes some kind of abstract space and then builds up a series of discrete features based on points and lines between those. And that enables us to create points or lines or polygons, which are essentially lines that end where they started and have an inside and an outside. They're very good vectors are very good for structured representations because of their discrete nature. So it makes it easy for us to select somewhere within a space or to select a point and then associate a bunch of attributes to that entire thing. They can be quite compact data sets. Rasters take a very different approach, and they divide space into a series of equal cells, so a grid of different cells, each of which will record some kind of variable that is typically a continuous variable or a combination of continuous variables. The most common way in which you will have encountered rasters before are as digital photographs. So a digital photograph really takes the light coming into the lens and divides for each cell will store some kind of something like a red and a green and a blue variable. But we can do something similar if, for example, we're interested in recording elevations. So these, because they need total coverage, or generally speaking, very even if parts of the grid can be masked out, they can often lead to being quite big data sets. And indeed, as we cover a larger area on the one hand, or increase the resolution, then typically we don't just double the size of a raster, but it's doubling in both directions at the same time. So we're quadrupling in size. So it's going to be an exponential growth in that raster size as we get bigger and bigger. So when we're working with rasters, we often have to think quite carefully about how big and how high resolution we want to work with for purposes of processing or storage. It's a question of choosing the best method that's going to fit whatever it is that we want to achieve. So we can bring within a GIS a series of different layers together, composed of these different kinds of vector and raster data. So we don't map all of the different aspects of the complex and messy world together at one time, but instead we divide those up into specific themes which try to capture a specific part of the world. So here we have an example of the real world. We have a river dividing some kind of a commercial sector of a city and some kind of residential sector of a city with some parkland behind it. And somebody has come along here and then created a series of different layers using both vector and raster data to try and capture different aspects of that messy real world. So one of the rasters has described or tried to classify it. So each of those cells is divided into things which will say this is a specific kind of urban environment or aquatic environment or a residential one. So those will be discrete variables. The second raster will have a continuous variable that shows the elevation. So we need to remember, of course, that in each of these cases, it's not the color or the wobbly shape that we can see with the elevation that's being saved here, but just some kind of numeric variable, which is recording that value. In addition to those, we have vector data, which is capturing the, first of all, in polygons, a series of areas of land ownership, of land parcels, then a series of lines, which show the streets within the city and district, and then a third one for customers. It's important to think here, especially when we're reusing data, that whilst we typically label our layers in ways that say streets or customers or parcels, we're often recording a proxy for the phenomena that we're interested in. So the example here of customers is important because, of course, it's not recording the customers themselves, but rather where the customers themselves happen to live. And those customers, those people, may only be at that place for a specific point in time. So whenever we work with GIS data, we always have to think to ourselves, how has this data been created and for what purposes? And do they fit the particular purposes that I want to put them to? To be able to associate all of this content together and to sort of see it and to be able to compare in terms of the geometry, in terms of the locations of these different kinds of data, then that content has to be georeferenced. So it's not enough just to have a nice picture here, but we have to understand the specific place on the surface of the Earth that each of these cells or each of these points or lines or polygons are, so that we know exactly between them where one overlays the other. And that turns out to be a harder task than you might imagine, because the Earth, contrary to popular belief, is not a sphere, but is in fact a kind of big wobbly ball of boiling mud hurtling through space and spinning as it goes. And that leads to an object where it's very difficult to say or mathematically define exactly where things are. The fact that the tectonic plates on top of it, the crusty part on the surface of that mud, are moving as well, only aggravates that. So whenever so the only way to do this is to create some kind of or indeed multiple kinds of geodetic system that will enable us to plot points in space. To do that, we have to get away from the topographic surface, the physical surface of the Earth, which, as you can partly sort of see here from this exaggerated example, is very difficult to know which way is up and which way is down, because most of the surface of the Earth is not orthogonal, if you will, to lines coming from whatever its center might be. But we can generalize to something called the geoid, which very roughly you could think of as is the period where global warming has gone into overdrive and the world is covered in water, and then the what's the word? The gravitational pull on that water will lead to something that is much more sphere-like. But it's still not a perfect sphere. So from there, we have to get even more arbitrary by creating what's called an ellipsoid, where we generalize for different points in space to try and get the best match for the surface of different places. So if we look at the example we have here of an ellipsoid, then in Europe, it matches quite well. But in North America, it doesn't work so well. And for that, we would need to generate another ellipsoid, which we can define mathematically. And for that reason, there are a number of these different geodetic systems available. And every time we record data, we have to be clear which of those geodetic systems we are using. Now, fortunately, though the math is complicated, Geographic Information Systems will do the mathematical conversions for us as long as we are clear to them which particular system we are using. Most commonly these days, especially for large global data sets, the geodetic system that you will kind of come across is called WGS84. But if you're working within a local context, then you may well find that that is specific to a particular country, for example. So within the United Kingdom, the Ordnance Survey uses one that's called OSGB36. And if we're combining those different data sets, then we need to be aware of the difference between those different systems, tell the GIS that that's going on, and then let it work out the maths. As well as the issue of geodetic systems, we also have to face the same challenge that Ptolemy faced, which is one of projection. How do we represent a sphere on a planar surface? So if you think about the problem of peeling an orange and then trying to flatten out the peel without it sort of springing back up from the table, you'll find, of course, that this is a difficult thing to do. There are various different ways in which this can be done, and here I'm just giving two examples to show you just how different the outcome can be from even ostensibly quite similar approaches to doing this. So one of these example projections is called a Mercator projection, and you can think of this as taking a ball, so take a golf ball, for example, and wrapping it in a cylinder. So let's imagine that we're just using the tube from a toilet roll or something. So then, if we imagine that that sphere is the Earth, and we take a line from the center of the Earth, and we take each point on the surface, and then draw it out, and so that the line, so sorry, I should say the crucial thing here is that the Mercator projection requires the tube and the ball to touch at the equator. If we do that and we draw a line out through the surface of the sphere onto the tube, then as you'll see in our example here, that with close to the equator, we can expect a fairly accurate representation of the Earth. But the further we get away, the more from the equator, the more stretched out things get. And of course, we can never really map the North or the South Pole at all, because if we draw that line, it will always remain parallel to the sides of the tube. But if we do that and then we cut the tube in half, then we get a map that looks like this, and is for most of the inhabited parts of the world reasonably okay for generalized purposes, which is why the Mercator projection is so commonly used for world maps. But if I'm interested in places, if I want to be more accurate about particular places, and I'm not concerned about trying to represent the world as a whole, another approach I can take is what's called the transverse Mercator projection. And that really takes a very similar approach, but rather than using the equator, in this particular example, we're wrapping it around the prime meridian, and in each case we would use a particular meridian. So in that case, the places which are along that meridian, in this case, say for example Britain, and much of Europe is much better represented, or much more accurately represented. The further we get away, east and west, the more distorted our representation becomes. So in this case, for the transverse Mercator projection, we can map certain parts of the world quite well, and if we want to map other parts, then we can move our tube around to the particular meridian of interest. So depending on the purposes that we want to map something for, a Mercator projection might work best, or a transverse Mercator projection might work best, or indeed there's a whole variety of other exciting projections that people have invented for particular purposes. Okay, so that's some background to GIS. Now I'm going to switch to a GIS itself, just to show you briefly how it works, and then I'm going to hand over to Alegria, who will give you some more ideas about what you can do with it. So this is the map view of a GIS, and we're going to see some data, some of which you'll have seen on those slides previously. So we might want to start with something that gives us elevation for a place. One possible source of that is the satellite the shuttle radar topography mission, which provides us with a raster of data, a very high resolution. This is actually quite a coarse data set of the whole world, but you can actually get this data up to 30-meter resolution. And here we can see this is northeast Scotland has popped up, and the darkness of these different cells here represents the elevation. So if I now use my identify tool here, oh, I don't know what that's done there. We should ignore that red line for the time being. We should see, oh, that's not giving us a pop up. I don't know if this is possibly because I'm in full screen. Let's see. That works better. I don't know if this is because I'm sharing with Google Hangouts, so we're not going to get a pop-up dialog. Okay, so you'll have to try this at home, which you'll be able to do when you use the exercise, which is in the wiki. Okay, so we can look at this. This is the data. We can change this data in different ways. So we can change not only the degree of darkness for particular heights, but we could change this, for example, to an entirely different color ramp that might show different heights. So we could have things at sea level, perhaps in a green or a blue, and things which are mountains or above a specific altitude in brown. But of course, it's a false color. The actual color of such a map would bear no specific relation to the true color of the territory itself. For that kind of thing, we can use something like Google Satellite, or indeed other mapping tile technologies. So we can bring in a lot of the really great web-based data to give us some kind of context that we might want to look at data for. We can zoom in to particular areas. So let's zoom in like this. You'll have seen the SRTM data flash up there, and that's because it's trying to overlay one over the other. Sometimes it takes a moment to refresh, and you have to sort of jiggle things around a little bit. So this is satellite data. Satellite data isn't interactive, however. It is essentially just a picture that we can contextualize content against. On top of that, we might be interested in other kinds of features. So here we have a shapefile. Shapefiles Tom talked about last week very briefly, and those are perhaps the most common kinds of data that you're going to come across for vector features. So here we have some river data that we can overlay. So now we can see much more clearly where the rivers flow in this space than we're able to do with satellite. I often find, however, that it's quite difficult to visualize where one river ends and the others begin, right? Because the rivers themselves tend to look very similar. So looked at from a great height, let's go back, get more territory here. We can see that it starts to become a bit of a tangle that's difficult to interpret. So what we might want to do is, rather than looking at the rivers, we can look at watersheds. So we'll take a moment to load, possibly. Great. Okay, so these are the watersheds, which are on top of the rivers now. If I, let's hopefully this will, we can bring attribute tables. Great. Okay. So I can now change the colors of these different watersheds if I want to. But here, just for experiment, what I'm going to do is, because I want to see both these watersheds and the satellite the satellite imagery and the rivers, I'm going to change its transparency. So let's change that to 75. And great. So now we can see the rivers, we can see the different colors of the river basins, and peeking through that, we can see the satellite data as well. Because those colors kind of bleed, I'm just going to throw on an extra red line here, red boundary around those watersheds as well. There is a huge amount of additional data that we can find online. So one of the things we might want to do is embed data from some kind of external source. So, oh, that's back to the screen. That's not what I was looking for. Is the sound okay? Is this working all right so far? Yeah, getting a nod from Gabby. Great. So let's see. Great. Okay. So there are a number of different data sources. Here is one from the David Rumsey map collection. So this is a really wonderful collection of historical maps. And you'll see, if you search the collection, that if the map has been georeferenced, so if we know where that map is based, then you'll have a link like this that says embed OGC WMTS tiles. If you select that link, it will give you instructions on how to include that within a whole range of different applications. So we're going to do that here. And we'll load that. So this is also just like the Google satellite being loaded in, and there it is. So we can sort of see that now overlaid. Okay, but that's now obscuring our other data. So we might want to bring that down here. We should be able to overlay that as well. And you can see the degree to which it's, to some degree, the degree to which it's accurate. One thing to bear in mind when you are georeferencing not only historic maps, but indeed any kinds of maps, is of course you're only setting a specific number of control points, and the spaces in between those have to be calculated automatically. And that can often give issues with what are called boundary effects. And up here, where we're going to look in a moment, let's see if we can zoom in there. Oh, let's go back. May take a moment to load. Great. We'll sort of see that once we zoom in, some of these things are not quite in alignment, and that's partly because of the places that there will be particular control points which will be correct, but other places will be mathematically calculated. Okay, so we're almost done in terms of our examples here. We can get rid of this for now. If you want to bring data in into a GIS without creating shapefiles, a really simple way of doing that is with CSV, again, which Tom talked about last week, comma-separated values. So here we've got some data that I've downloaded from the rather wonderful Canmore database of sites of large hill forts in the northeast of Scotland. So again, if we look at that, our attribute table, here are the different places. And this has an easting and a northing. And when I import that data, I can specify that one of these is an X coordinate and one is a Y coordinate. And I also need to specify that this is using the OSGB36 coordinate system rather than the WGS 84 one, which the map project itself is generally using. So last of all, so going back to forest here, there are other kinds of data like LiDAR, more sophisticated kinds of data. Let's zoom to our layer here. So here is a series of hills by this particular town. And GIS enables us to process that data in ways that can enable us to visualize it in ways that are a bit clearer. So here I can just about make out a series of paths that loop through these particular hills, but I can use a method here. So here, this is our raster menu. There are a variety of different kinds of tools that we can apply to this, but we can create a colorized slope. So here we're calculating the value, not of the height, but the calculated angle between two different points of elevation on the raster, and create a new raster from that. And if we do that and we colorize it, then here we can start to see those lines much more clearly than we can if we're just showing the areas in grayscale. Sorry, just showing the elevation in grayscale. Okay, I'm going to finish there and now hand over to Alegria, who's going to talk a little bit about some other possibilities of using GIS before kind of coming back to talk about a little bit about the some things to think about when you're using GIS.
Alegria is having network problems at the moment, so she will attempt to rejoin us as soon as she can, but maybe we could skip on to the next part.
Great, yeah.
Come back to her in a bit.
Okay, doke. Great. So, okay, so she's a GIS in action. So, some issues to think about when working with GIS. So, one of these is, and this is really, in particular, when we're thinking about GIS as a tool for analysis, it's certainly true that the kinds of technologies, and especially web mapping technologies that we've been discussing earlier in the course, can be used for analysis as well. But most commonly, they have historically been used for purposes of dissemination. And so there's something you want to information that you want to pass on to other people, and that's the raison d'etre for using it. Whereas GIS, more typically, has had a focus on analysis and then producing maps. For producing paper maps, most commonly in terms of dissemination. So some of the issues I'm going to talk about here are focused a little bit on that analysis. But again, to underline, there is a huge amount of overlap between what you can do in GIS and what you can do with web technologies, and that overlap to some degree is ever continuing. Okay, so the first of the things we have to think about is an issue of what we might call pseudo-totality. And that is a problem that when we look at space, it's very tempting to, or very difficult often, to tell the difference between the absence of something on the map and the absence of something in the world. And often the absence of something in the map has got nothing to do with whether or not it's actually there, but simply the fact that we don't have any information about it. So essentially we don't have total information, but the map requires us, because of the way that it's constituted, to try and say something about it or risk being misinterpreted. Now this, of course, is not a new problem, and here is a great example of an early map of the Americas where you can see up at the top that lots of the blank spaces are being filled with other kinds of stuff to try and take away from the fact that there's nothing for them to put there because they don't know what's there. So to use the old archaeologist sort of saw, absence of evidence is not evidence of absence, and that's really true when we look at GIS. So when you're using a GIS, so whenever you work with data, one of the most important things you can do is ask yourself, how has this been constructed? What might the gaps be? What might the biases be? And not just look at the patterns on the screen, because those patterns will, at least in part, be defined by absences caused by things that have got nothing to do with the phenomena that you're interested in. Another issue with GIS is the primal or the primacy that it gives to geometry. So essentially with the GIS, it's not every attribute of you're using, everything that's being represented spatially requires some kind of spatial information associated with it, to the extent that the geometry itself is pretty much the primitive thing that all the other content is associated to. And that can make it surprisingly difficult to align content together computationally. So it's very good if we think about that layering system of being able to look at two different layers and realize that one thing and the other thing are basically the same. But computationally, that can be harder. Here's an example, right? So we might have two different entities that we've brought together from two separate data sets. They both have very similar geometries, and they both have names which are very similar, but of course the identifier for them is different. As a human being looking at this map, I can, with a reasonable confidence, assume that these are basically referring to the same thing. The problem comes with when we realize that the computer doesn't understand this because of issues of scale. If we zoom in, then there is a genuine and very real difference between two different places. Let's say number 1 and number 2 on this map here from GeoNames. If that's the case, the computer there is no possible principle on which, other than one which we arbitrarily define, for the computer to know that these two places, because they are close together and have similar names, are in fact the same thing. Okay, so we can use various buffering mechanisms and say, okay, well, take any two things, irrespective of other attributes associated with them, and if they're close enough together, assume that they are the same. But of course, that doesn't always work for us, because at some scales, it's really important that we separate things which are quite close together. Okay, so using geometry can be very powerful in terms of us, in some kind of heuristic fashion, realizing that we're talking about the same or similar features, but at a computational level, it's actually quite difficult. Also, the need to associate things with specific places in the real world means that it can be quite difficult to deal with things like unknown locations. Frequently, if we're working with the ancient world, we know of the existence of a particular place. We know it because we have coins that come from there or historical testimony. We just don't happen to know where it actually physically was in the world. And for that, GIS, this is one of the problems that Tom raised last week, it can only get us so far. We can talk about that place, but we can't put it on a map because we don't know where it is. Likewise, we might know where the center of something is, or indeed parts of a region, but we might know where the boundaries are. However, that geometric primacy is largely based on having a boundary. A polygon is not so much defined by the bits in the inside as the line around the outside. So if the line around the outside is unclear, then it's very difficult for us to represent that without using some kind of proxy like a point. But points, especially for large regions, can be extremely misleading. And places, of course, which are mythical or fictitious or not on Earth in some other kind of way, are also very difficult for us to work with in a geographical information system. A further problem, Tom really nicely called this Pleiades gazetteer, and Barrington, I think actually, a long exposure snapshot. And all GIS systems, generally speaking, all spatial data tend to be one of these sort of long exposure snapshots to one degree or another, perhaps not to the same extent as the Barrington, but almost all data is recorded over a period of time. And that, unfortunately, that period of time is rarely very clear when we're looking just at the 2 dimensions that we work with in GIS. So it's very easy to be seduced into looking at a nice map like this that shows some kind of historical territory and the settlements within it, and think, great, well, here's the province, here are the places within it. But if we looked at where the sources of information from which that data had been compiled, we might well find that those all come from distinct periods in history, and it may well be, for example, that the point down here at the bottom, this little settlement down there, disappears long before the one up at the top of this diagram appears, or perhaps that the boundary on the right-hand side had moved long before we recorded the one up at the top. Okay, so this is not just the case with historical data. If you think of the data that Google Maps provides, Google satellite data, that itself is, of course, compiled from data collected over different years, in different seasons, as different buildings or indeed kind of cities can rise and fall, and yeah, all sorts of different things can be can affect the way in which we interpret that data. But of course, those the things which cause that are rarely very transparent when we're working with a GIS or working with that kind of data, almost intentionally so. One of the great kind of post-processual critiques of using GIS is the tendency for it to give us a kind of God's eye view on phenomena, which of course were experienced in a radically different way by the people that we might be considering. So we can look at here the south of France and see the ways in which that landscape is carved up by different rivers and coastlines and mountains. But if you were somebody in that landscape 1,000 years ago, your understanding of it might be very different, and it certainly may well have been largely caused by your experience of being in that landscape itself, seeing those mountains in front of you, encountering rivers, and so forth. And not knowing what's over the horizon, or not in any great detail. So whilst it can be helpful for us to understand specific phenomena, we also need to be aware that it can be taking us away from other kinds of interpretation, other kinds of information that might help us in terms of understanding what is giving rise to particular human behaviors. And related to that is the issue with proxy data and ETIC classification. So we tend to break down the world into categories and classifications that make sense to us. So here is the really wonderful mapping tiles produced by Johann Alfeld for the Digital Atlas of the Roman Empire. And one of the great things about it is it shows us the network of communications between places based on the evidence that's available to us. But of course, that network is composed of all sorts of different kinds of information. It might be archaeological information, it could be itinerary data, it could be something else entirely, it could be sensor data or satellite photography and the like. So our looking at that and treating it as a single network might not take into account different ways in which the people moving around that landscape might have understood that network. They might have broken those down into very different kinds of phenomena. And finally, GIS, although this has improved over the years, still tends to be quite application-centric. It still tends to involve the use of desktop-based software and the use of particular files within it. Now, that gives us a great deal of flexibility when we're working with geospatial information to manipulate it and analyze it in ways that suit us. But when we're sharing that data, then unfortunately the tendency here, so we've got Alicia, we've got Boris, and Boris is really interested in Alicia's data, and Alicia says, great, well, I'm happy to share it with you. So of course she then makes a copy, which she gives to Boris. But if Boris then changes that data, it now becomes unclear, which data should be used for which purposes. Should he give it back to Alicia? Or is it better for Alicia to work with her data? And what happens when Charlie comes along and wants to use the similar data? Which should they use? Okay, so that tendency for files to proliferate, and those of you, those who work with GIS will all tell you that they have a tendency to working with all those files can often be a challenge. So some concluding thoughts, because we are now, I think, this has been about an hour, unless Gabby wants to kind of go further, are that spatial analysis should never be an end in itself. Okay, it should never be something where you think, I've got some spatial data, I'm going to analyze it. Okay, you should never be driven by that kind of motive. It's spatial data and the tools available to us are fragmentary, and all of the words here: contingent, subjective, deceptive, sparse, and seductive. And it's very easy for us to be taken down rabbit holes that are utterly misleading in terms of our understanding of the past. However, at the same time, they can be an incredibly powerful means for sorting, sifting, contextualizing, connecting, presenting, but above all, provoking new ways of thinking about the past. So when we're working with this data, we have to be aware of its limitations, not just of GIS as a software, but the data as well. But that doesn't mean that it shouldn't challenge us and make us think, hang on, what I'm seeing here seems different from my understanding of what's kind of going on. And then trying to follow up in all the ways that we possibly can to try and establish, is there a real phenomenon here? And if so, what is causing it? Or is it merely an artifact of the particular approach, the particular data that I've taken? So no single tool is capable of resolving the many issues in spatial analysis. GIS is just one of them, and you guys have encountered a number of others. There are a very wide range. It's a really wide and interesting, expanding field, and I would encourage you to explore it widely so that you can find the tools that are best suited to your particular interests and needs. And I will finish there, only other than to say that within this PowerPoint, and soon to be uploaded to the wiki, I've added some information. I'm going to flick through here. So there are two very commonly encountered GIS software packages: ArcGIS from Esri and Quantum GIS. Quantum GIS is open source. ArcGIS is not, but they're both excellent in their own ways. And I would encourage you to use whichever suits your needs best, and your wallet, of course. And then here are some information about where you might find freely available or usually freely available data, satellite and road data, map tiling services, things like hydrography, which is and other kinds of environmental data, which is often very good in Europe these days. And historical data sets, those are usually much harder to come by, but there are a number of places you can get some content. You may well have to create your own. Elevation and LiDAR data, again, is very kind of raster data of other kinds. Elevation is now...
You're breaking up quite a lot.
Gabby,
your audio is breaking up.
Oh, I'm breaking up. Okay, I'll finish there. Other than just to say, here's the good stuff. Go find it. And that's me. Hello?
Thanks a lot for that, Leif. Yeah. I'm sorry we lost her in the middle. She just emailed me to say that she's managed to get back online. I have to. I'm hoping.
Oh, do I?
But for example, I know as well. Used.
Sorry, you broke up there a little bit. So
thanks for that. Thank. So maybe maybe or before we do, does anyone want to any questions or comments from anyone else on the Hangout, or for that matter for anyone else here in Barcelona? Want questions or make any comments? Any observations? No? Yes. Maybe yeah. If you come here so we can hear you. Yeah.
Hello, Leif. Thank you very much for this excellent presentation. I'm Dani Akish. I was wondering during your talk how many of these limitations of GIS were due to the fact that it's geography, and how many are due to the fact that it's digital geography. How many are due to its digital nature? And my hunch was that most of these problems are probably inherent in any kind of mapping.
Yeah, I mean, it's certainly true. That's a great question. And I think it's certainly true that, things which aren't mappable aren't mappable in some ways. But I think there are a variety of other kinds of approaches, things like network analysis, some of the things which are being done in linked data and gazetteers, and other kinds of I guess more kind of conceptual approaches to space that are still spatial, and indeed can still be kind of considered geographic, which don't fit quite so well with GIS. So I think GIS has been partly very successful because it has these well-established frameworks based on vector and raster data that an awful lot of people in an awful lot of fields have been exploring different ways of exploiting for decades now. So that makes these very, very sophisticated tools. But I think at the same time, GIS, at least of this kind of relational raster and vector type data, is also has these limitations, which are partly based on their history, on the fact that these software was developed to work with these specific kinds of data set. And although I think things are improving, so you do find that the GIS software houses these days typically are more supportive of, say, web-based formats than they used to be. Not that long ago, you wouldn't have been able to get KML, for example, into a GIS or derive data from a web server unless it was one that was offered by a particular software house. I won't name any particular names here. A kind of a notion of trying to have a kind of a closed ecosystem of content. I think that's changed over time and really improved. But we've still got some way to go. In my own kind of interest in linked open data, where there really is no support for things like RDF or URIs in quite the same way, and I'm looking forward to a time when that comes along too.
Great, thanks, Leif. So anyone else had any questions or comments to add? Anyone else in the Hangout?
Can I add something? So I think that in this regard is important, Leif, your last concluding thought, so that no single tool is capable of resolving the many issues. But this is not only about spatial analysis. This is something that I think we have been learning in the digital humanities. Yes. So we definitely need to make use of different approaches, but this is something that we have also learned studying history or philology. Of course, now we want to look for standards, common tools, but definitely we need to explore many different possibilities. And so this is not only for geography, but for many other topics. So.
Yeah, I couldn't agree with you more. I think there is, I think there are understandable reasons for this, but I think digital humanities, unfortunately, has often fallen into or practitioners often fall into kind of the golden hammer syndrome, right? They become an expert in a particular thing, and when all you have is a golden hammer, then everything looks like a nail. And yeah, we need to get beyond that. The tools, and indeed, of course, whilst also accepting the digital itself, right, it should only be in a healthy kind of humanistic approach, a part, and frequently only a small part of what enables you to marshal an argument or raise a series of questions in the humanities. So the fact that it's essential doesn't, it may turn out to be essential as part of that, doesn't mean, of course, it's the whole picture. It may, in fact, only be a small part of it. Yeah, thank you for bringing that up. That's, yeah.
And all of that was true before there was any digital at all, right? That was equally true of the various different analog approaches we take to geography, to history, to text, or whatever. If all you're doing is one particular critical approach to something, you're missing 90% of the story, guaranteed. Yeah, it's always true. Yeah. Any other comments? We started a few minutes late, so we can keep talking if we want to. But again, we should only use the tool of talking more if it's appropriate to our ends.
Yeah, I think. I mean, I'll kind of mention. So there's an exercise on the wiki. There's a couple of example data sets which are linked from my Dropbox if you want to use those. But I would really strongly recommend that you try. There's so much spatial data out there these days. Try and find some content that's relevant to your own interests and explore with that. And it takes the other thing is that, I mean, it is a big field, but the documentation that's associated with it is also really excellent. So these are not leading edge technologies in the way that much of the stuff that you encounter in the humanities often is. It's a tool developed by a humanist when they had some funding available and so on. When you come to GIS, this is a technology that's used in a very wide array of fields. It's been around for a very long time. Software, both ArcGIS and QGIS, are developing rapidly and continually adding new features. And they have huge user support groups. So the documentation is excellent, forums are excellent, and so on. So I would definitely, if this is of interest to you, because it's not something that you can just sort of necessarily pick up and use effectively overnight, but if it is of interest to you, there is loads and loads of resources available. And I would certainly start with the kind of vendor documentation pages, which are often very, very good.
And Isa points out there is, of course, documentation in Brazilian Portuguese and in many, many other languages as well. This is not.
Yes. Yeah, that's great. Yeah, that's correct.
Yeah, great. Cool. Well, thanks a lot again, Leif, and thanks again, everybody else. I'll just mention very briefly to finish that next week's session is on data. What's the exact term? Data structuring. It's on ontologies and data modeling is the expression I was looking for. And so Ariana Chula and Charlotte Tupman will be joining us next week to present on that. Again, the page on the wiki has some preliminary reading and some exercises that will follow on from that. But in the meantime, I encourage you to follow the exercises that Leif and Alegria have given us on this week's session. And thank you very much. See you all next week. Bye.